Okay, so this is Team 15, the second project, designing a belt buckle. Current members here. The table of contents here is just, we're going to go through the introduction, assumptions, the free body diagram, hand calculations, the FEA, comparison between the two, conclusions. Alright, so in this project we had to come together to design an initial seatbelt buckle that would withstand a certain amount of forces in a race car. After that, we had to optimize the design, check for a safety factor, and make it as lightweight as possible. To do this, we had to do hand calculations and also FEA through software to get the optimized belt buckle for our final design. Assumptions we made here, the material that we were able to use on SolidWorks was this titanium alloy with the following properties here: yield strength, tensile strength, and the ratio. We also made an assumption that the buckle is symmetrical and that the bolt hole will be fixed to the car, so that would be a static. And we also make an assumption that the force given to us is equally distributed among the 6 belt buckles of the 6-point harness. This is our free body diagram here. You can see the known forces would be the pink arrows, where the seatbelt strap would actually be displacing the force. The green arrows at the bolt hole represent a fixed structure where it would be attached to the car. These are our hand calculations right here. First, we had to calculate the force on each buckle, which was given that a 200-pound man subject to 100 Gs, and each of those is the force is dissipated evenly into the 6 belt buckles, giving us a force of 3,333.3 pounds force. We also, to do the SCF calculations, we make an assumption, split it up into 2 parts. The first part being the circular hole with the following width and diameter and thickness. From that, we get our area, and using an SCF calculator, we calculated a KT of 2.24. After that, we find our nominal stress using the force that we calculated over the area of the circular hole section. After obtaining that, we can get our maximum stress at the bolt hole section, which we got to be 31,438.28 psi. After that, we move on to the slotted section, using the forces and the dimensions that we initially had, and calculating the stress using the SCF calculator. Once again, we're able to calculate a maximum stress of 51,373.44 psi. Right here, we're just checking for safety also. Put our ultimate tensile strength over our maximum, which is at the slotted hole. We got a safety factor of 2.96, which is well above our 1.5 safety factor. On the bottom left corner, it's just calculating the maximum stress that the model would be able to take, assuming the 1.5 safety factor. We did try the optimization that was in the books of the chapter, which is what we're trying to do here. We did run into a few problems with the optimized new dimensions. It would not pass our safety factor, so we moved on to do a sort of a trial and error in order to change the dimensions. After this is the final design that we decided on, we kept noticing that the slotted hole was giving us the most problems. So one solution we had was to add more material at those particular sections. With a thickness, from being a simple 1 thickness solid plate with 0.31 inches of thickness. After that, we added just 2 circular extrusions shown at the slotted hole, and the total weight at those extrusions was 0.56 inches. So as I mentioned before, these are loads and constraints that we assumed on our seatbelt buckle. The green arrows represent the bolt where it's fixed to the car, and the pink arrows represent where the force is actually being exerted by the seat belts. We also experimented with the mesh sensitivity, which is shown by the following tables. The mesh size, the smaller the size and tolerance, then the more accurate and the more finite the elements of the mesh would be. So in other words, it would just be the smaller the little element sizes, the more it's able to calculate. As you can see by the table, the smaller sizes typically have more accurate and higher max von Mises stresses. We decided on the mesh of 0.05 because it was a fine mesh, but it was easy enough to work with. We also tried changing the mesh around the areas of interest, which again were the edges and the inside of the circular slot. This right here is the von Mises model that we ran through the FEA on SolidWorks. The top picture you can see areas in blue. Obviously, we're going under less stress than the green, and the green less than the red. As mentioned before, that's the area that we experienced the most stress with, which is why we added the extrusions to our model. Below that, we can see the safety factor plot. This would show anything that's above our specified safety factor, in this case 1.5. Everything that's above that would be depicted in blue, and anything below it would be depicted in red. As you can see, nothing's in red, so we were above our safety factor for all of our buckle. According to SolidWorks, our weight was at 0.04 pounds. So after comparing the hand calculations with our FEA, it did correlate that the slotted hole area was the one with the experiencing the maximum stress, which is what we expected through our hand calculations. The values, like I said, they were different. That had to do a lot with the mesh. Also, in our assumptions, we were separating the buckle into two separate elements as opposed to just taking the buckle as a whole. So this can account for the differences in values that we had for our stresses. But we did find the area was the same for both hand calculations and the FEA analysis. So in conclusion, we got together. First, we had to come up with the design. So we had various prototypes, which were not shown here, starting with bigger, moving things around and different shapes. Finally decided on the shape of our buckle here, after which we ran the analysis, noticed the points of interest, and we were able to optimize our design in order to meet the factor of safety that was given to us. Once we decided on a final design, we went ahead, did the CAD for it, ran the analysis, calculations, and we ended up with our final buckle. Some of the challenges we had were just learning some of the software and calculations to go with it. Initially, we made a mistake calculating the force, which gave us a much larger force, which did not seem reasonable. So we looked into it and realized that we were doing something wrong calculating the force of the man. Our force that we were calculating before was way too big because we were not taking into account that the weight is already taking gravity into account. So once we figured that out, it let us make our design much more smaller and efficient, and we were able to modify it from there to meet the factors of safety. As far as shape optimization, SolidWorks did give us hints through their shape optimization feature in their simulations tab. From there, we also did a sort of a trial and error. We noticed, the edges, of course, would have more stress concentration as opposed to rounded off edges or filleted corners. So that is why we decided on the roundness at the corners. And instead of a square slot, we decided on the circular slot for the seatbelt. And through that, we were able to optimize our design and end up with our final buckle shown before.